All right, there we go. It's going to be recording. Usually when I post records of any of the Zoom sessions, I have a YouTube channel where I post my videos. I'll send you guys the link to that later if you'd like to see any of that stuff. Also, I have a few series videos on there for when we get to the part of the class that uses that, so that might also be a good review on there. But anyways, so what I was talking about before I started recording was we have all these different methods of solving equations, and oftentimes more than one will apply to a certain equation. So in that case, how do we know which ones to use? And so I kind of have like sort of like a ranking for which ones to prioritize. So I would say that probably the easiest one to do is separable. So if you see that an equation is separable, and all you have to do is just move the x's to one side, y's the other, and do an integral, which usually isn't too bad, and then you're done. So separable tends to be definitely one of the easiest methods for solving equations. So if you see something separable, I recommend kind of just diving into that and doing it that way. Two other methods, which I think are about equally as hard, are exact equations and linear equations. So both of these end up being relatively simple to do once you get used to them, though they do require a little bit more work than separable equations. Like for exact, you have to check that those partial derivatives match up, and then you have to do two integrals, which are really the same function. But usually with exact, they're easy to identify because they're already written in the form where we have something times dx plus something times dy. So this is easy to identify and not too hard to do. Whereas with linear ones, it's very procedural. So you kind of do the same thing every time. You put it in linear form, find the integrating factor, multiply it, rewrite as a derivative, and then integrate. So usually linear equations aren't too bad to solve either. And they're not too hard to identify either. You just need to make sure that the derivatives or y's really aren't squared or anything like that, or they're not multiplied by each other. So usually these guys aren't too bad to do, but I think separable tends to be a little bit easier than them. But all three of these aren't too bad. The next row I would say would be exact with integrating factor. So in lesson 8, we saw that some equations were almost exact, but not quite. We need to multiply it, the whole equation, by something first, and then it'll end up becoming exact. And naturally, it's a little bit harder than exact equations because you have to do an extra step. And kind of in the same way, I would also classify Bernoulli equations in here as well on this kind of like third tier level, because Bernoulli equations, you end up turning those into a linear equation by doing an extra step or a substitution, and then you just kind of go back up here and do that. So these are kind of the same as these ones, only they require an extra step to perform. So I would only kind of do these if you really need to, and ideally you would hope that your equations end up being like this. But if you really need to do these, then I guess they're there for you. The one method that I wouldn't use though, unless you really have to, like it's the only choice, would be homogeneous equations. So where we often see a bunch of x's over y's or y's over x's or things like that. So that has a pretty clear way to do it. You use v equals x over y and do that substitution. But oftentimes the integrals you get for that are really bad. So you'll often get a lot of like integration by parts or partial fractions, or God forbid, maybe even some trig sub coming from those integrals. So I try to avoid doing the homogeneous method if it's any of these other ones. But unfortunately, sometimes an equation is only solvable by the homogeneous method, at least among the methods we know. So you're kind of forced to do in that case. So I would consider this as like a last resort. If we really need to do it, then I guess we have to do it and do probably a trickier integral. But this is kind of like my my ranking list for prioritizing which equation to use when. So this isn't like a hard rule. This is more of my personal opinion, but I think most people who either have taken this class or have taught it before or know differential equations would probably agree that this is a pretty good tier list for which methods to prioritize when. All right, so that's what I have to say about that, at least. let's see. So I have a question asking about which integration method should we know for the upcoming exam. And as I said the very first day of class, solving diffie-qs, you either guess, you integrate, or you do a computer. And so far, we've seen a lot of the different integrating methods. So let's talk about the integral methods that we definitely need to know for the upcoming exam here. So let's see. Integration methods. Okay, so you definitely need to know how to do pretty much any Calc 1 integral. And what I mean by that is you definitely need to know the power law, like the integral of x squared is x cubed over 3. You need to know the things involving like sines and cosines, like the integral of cosine is sine, and like all the integrals of the basic trig functions. And then maybe like the integral of 1 over x is natural log of x and things like that. So that's kind of what I consider Calc 1 integrals. And I think hopefully most of you guys have that stuff down really well by now. But something you might be a little bit shakier on are maybe some of the Calc 2 techniques. Those were definitely a bit more involved and tricky. I guess something that was kind of on the border between Calc 1 and 2 is U sub. I mean, we definitely learned about it in Calc 1, but we really only master it when we get to Calc 2. And definitely U sub is probably one of the most common integration techniques we have to do. So make sure you're comfortable doing U sub. And one suggestion I would say for this is don't forget your du. So when we're doing a U sub, we need to figure out what du is and plug that into the integral as well. And it's pretty easy to forget about that. So don't forget about that when you're doing a U sub. Let's see here. So what other techniques might we need to know? A few Calc 2 specifically techniques that do show up are integration by parts, or IBP. We've definitely seen some integrals like x squared times e to the x where you definitely need to use that method in order to integrate. So that's definitely fair game for this test. This is also known as the tabular method because there's a sort of like a shortcut that involves making a table to do integration by parts. So you may also know it as that as well, but they're really the same thing. So that's definitely a technique I would review if you're feeling a little shaky on it. Let's see. Some things we've had to do occasionally are partial fractions. So that certainly showed up. It especially shows up with homogeneous equations. It's pretty common to have to do partial fractions for that. It also happens with separable as well. It's pretty common. So remember, partial fractions where we have some rational function, we split it up into multiple ones that are easier to integrate. So I would definitely say partial fractions. Now, we also talked about in Calc 2 like difficult trig integrals, like maybe like sine squared times cosine cubed. And I'll tell you right now, those won't be on the upcoming exam. So you don't need to worry about doing any weird combination of trig functions besides like some of the basic ones. Like you should definitely know how to do like, like the integral of tangent or something like that, but maybe not like cosine to the 5th times sine to the 4th or something. But I wouldn't worry about too much about that if you're feeling shaky with that. Also, another thing that we had to do on the homework once, but we're not going to do on the exam is trig sub. So I would say if you're feeling shaky about trig sub, don't worry about it too much. We're not going to have to deal with that on the upcoming exam. There is one more integral, though, that I'd really like to emphasize that is kind of important. And you might kind of think it has to do with trig sub, but I kind of view it almost as like a special case. So one integral I would certainly know is that the integral of 1 over 1 plus x squared is arctan of x plus c. This is an integral that shows up all the time. And you've probably already seen it quite a few times in the homeworks or the lecture quizzes as well. Technically, you could get this integral by knowing what the derivative of arctan is and then doing it that way. You could also do it by a trig sub with x's tangent of theta. But honestly, this shows up so often that I would recommend just memorizing this one. So I would definitely know this integral because this does show up quite a lot. But if you know this formula, then you don't need to do trig sub with something that looks like this. So I would definitely know this guy as well. This is going to be with us for pretty much the whole class. We're going to see that one a lot. Finally, I've also gotten some emails and stuff about which trig identities should we know. And I would say that for right now, just make sure you know the 3 Pythagorean identities, like cosine squared plus sine squared is 1. and then the other Pythagorean identities involving secant, tangent, cosecant, cotangent. Those you definitely make sure you need to know. You definitely need to know those guys. And I would also make sure you understand your unit circle if you don't already, like what sine of pi over 3 is, for example. Make sure you know that. But don't worry about things like, the double angle formula or like the sum to product. You may have needed to know a few of those for the homework, but that's where you can look things up. For the exam, we're not going to throw anything like really weird like that at you guys. So don't worry about memorizing the whole Wikipedia page for trig formulas. All you really need to know are the Pythagorean identities and the unit circle. That'd be what I would say about that. All right, so that's kind of like the integral and like trig background stuff that we need to know for the exam. I think we got a few other questions here. Let's see. I received a question. Are you the one that writes the exam, or does another instructor write the exam? So I've been recycling some of the questions from previous years for this 50Q exam, but I'm the one who selected the questions, I guess. So I guess the answer is kind of. They were written by someone else a while ago, but I'm kind of picking which ones go in the test. But the ones that'll go in the test will be usually pretty similar to the ones on the homework. So I mean, there won't be anything that's like, especially kind of a curveball if you've managed to go through all the homeworks, lecture quizzes, and now you try it and things like that. So I wouldn't expect anything too far out of left field as far as the exam goes. All right, let's see. So we also have a screenshot from a problem here. Let's see, let me open this up. Okay, so this is a question about solving a differential equation. So let's get down to it and see. Let's get some practice solving this. And by the way, even more so than other math classes, what we're doing in this class is we're essentially learning a bunch of techniques. Like there's a technique for doing separable equations, technique for doing linear equations, and so on. And as you do more and more of them, you kind of realize that each one is more or less the same every time. You kind of just do the same procedure every time. That's why it's important for you guys to keep practicing these methods until it almost kind of becomes boring. Like, oh, I know what's going to happen now. I have to get the integrating factor, then multiply by it, then do the product rule. Like once you start kind of feeling bored with the procedure, that means I think you probably mastered the technique. But it's important you guys practice until you get to that point. So let's start practicing now with this differential equation. I think this is from one of the homeworks earlier. We have xy plus 3x minus y minus 3 over xy minus 2x plus 4y minus 8. Okay, we need to solve this differential equation right here. Now, I'm pretty sure, oh, I also got another question. This is actually what I was about to address. Which lecture is this from? If I'm not mistaken, this is from the separable equations section. So I think that was lesson 5, if I'm not mistaken. That's what this one's from. But the thing is that if we look at this, this doesn't really look separable at all, right? Like this looks like just like a giant mess of different things. Our first guess might be, okay, maybe this is like one of those, maybe this is like an exact one or something. I would have to move this over here and then do partial derivatives. Maybe those would be the same. But this one actually ends up being separable in disguise. And let's see how that is. So what I'm going to do is I'm going to do an algebra technique you may not have had to use in a while, and that's called factoring by grouping. So we can do that when we have 4 terms and we want to try to factor this. Because my goal is to get this to be a function of x times a function of y. We can get there by factoring. So I'm going to look at the first 2 terms here, and I'm going to try to figure out what they have in common. What's the biggest thing I can pull out of these 2? And it looks like they both have an x in common. So I'm going to factor that out. And then what's left over from the things that I pulled out of are y and then a 3. And I'm going to do the same thing over here. Now, my goal with the second set of terms is to make the leftovers look exactly the same as the first set of terms. Now, this is already very similar to y plus 3. It's negative y minus 3. So I can make it into y plus 3 by pulling out a negative. All right, so we did that. We managed to get 2 copies of the same thing. And then on the bottom, I'm going to try the same technique and see what happens. So once again, I can pull an x out of these. And we have y minus 2. And then now my goal for the second set of them is to make that look like this. So I'm going to pull 4 out, and then that will also be y minus 2. And then finally, the last step of this factoring by grouping is that now that this negative and that x share these two terms in common, we can combine them together. And we have x minus 1 for the negative 1 times y plus 3. And then the same thing will happen down here. We're going to get x plus 4 times y minus 2. So now that we factor this and it looks a lot cleaner, we can definitely see that this is going to be separable because I have my x's right here, and then I have my y's right there. So now we could definitely see that this is a separable equation. Now, one thing that doesn't matter most of the time, but may matter some of the time, is that there are these things called, they have a bunch of different names. I think they mostly call them lost solutions in the notes, but they're also called extraneous solutions or singular solutions as well. Anytime we're doing a separable equation and the function of y could equal 0 somewhere, that will end up being a solution. So for example, for this one, since negative 3 would make this function be 0, if I have y equals negative 3 as my function, the derivative of that will be 0, and it'll be 0 over here. So this technically works as a solution. So there are some instances where they want you to find all of the solutions. So if they ask for all of them, you can't forget about these lost or extraneous solutions as well. So y equals negative 3 is a solution we can identify as soon as we know it's separable. But not all separables have those, like some functions of y right here aren't equal to 0. So sometimes we don't have them, but we need to be on the lookout for them. And one other question I've gotten about that is, oh, what about y equals 2, something that makes the denominator be 0? But it's only things that make the numerator be 0 that count for a lost solution. Y equals 2 wouldn't be 1. All right, enough about that. So that's kind of a minor point here. So now we're going to put it into separable form. So I'm going to bring all of the y's over here. So I have y minus 2 over y plus 3 times dy. And then I'm going to bring my dx up here. So I have x minus 1, x plus 4, dx. And then once we get to this stage, then we're just going to integrate both sides to undo these differentials right here. All right, let's see how we're going to do that. So we're going to do the integral of this divided by the integral of this. Now, technically, these are rational functions, and the degree on the top and bottom are the same. So we could technically do long division and then integrate the leftovers of that. But rather than doing that, there's actually a quicker way of doing it, which you may have also been taught in Calc 2, and that's called adding 0. And at first, adding 0 sounds kind of dumb, but if you add it in the right way, you can get things to cancel out. So for example, wouldn't it be nice if up here we had a plus 3 instead of a minus 2, because then those could cancel out? Well, we're definitely allowed to put one up there, so we could put a plus 3 in here, but we also need to account for that by also subtracting away 3 as well. So we're really not changing what the function is. And we could do the same thing over here. I would really like it for there to be a 4 up here, but I have to subtract 4 to compensate. So my integral now is going to be y plus 3, and then negative 2 minus 3 will be minus 5. And then on the other side, I have x plus 4 minus 5 as well over x plus 4. Okay, so then now that we have this going on, we see that we could do some cancellations. So y plus 3 over y plus 3 will be 1, and then I have minus 5 over y plus 3. And then the same thing happens for the x side. I have 1 minus 5 over x plus 4. Okay, and that would be the same result as if we did long division, but I know a lot of people don't really like doing that, so I like to do this adding and subtracting the same number trick to avoid doing long division. So now we can integrate these, and these are definitely in the Calc 1 territory for integrals. So the integral of 1 with respect to y will be y. The integral of this, since it's 1 over y plus or minus a number, will be natural log of that. So minus 5 ln of absolute value of y plus 3. And then meanwhile over here, the integral here will be x minus 5 ln of absolute value of x plus 4. And then I guess I'll just put the plus c over there. It may seem like, oh, we did 2 integrals, so we need 2 plus c's, but technically I could subtract one of them into the other one. So you really only need to have one. And by default, I usually put it on the sides of the x's. So you can do it however you want. All right. So the downside of this class being online is that all your exams are going to be multiple choice. If you were doing a free response question and you have this as your answer, that would be where you could stop. That would be totally okay to stop right there and just leave that as an implicit solution, meaning where we didn't solve for y. But I'm pretty confident if I remember this question correctly, you didn't see anything like this on the answers. So usually we might need to do some more algebra after we're done with the actual differential equation. So I think the algebra we need to do here and the algebra that we commonly need to do in situations like this is move all of the logs to one side and then use log rules. So I'm going to add this over here. I'm going to subtract the x over here. So I have y minus x is equal to 5 ln absolute value of y plus 3 minus 5 ln of absolute value of x plus 4 plus c. And then what I'm going to do is I'm going to use log rules to combine these. Actually, I'm going to move the plus c over here. I think that might be a little bit better. So then I have only logs over here. So remember, subtraction with logs turns into division on the inside. So I have y minus x plus c is ln of absolute value of y plus 3 divided by x plus 4, and then there's a 5 in front of both. And then finally, the other log rule that ends up being important is that a 5 or a coefficient in front of here becomes the power on the inside of the log. So we have all that stuff raised to the 5th power. And then finally, I think the last thing they did, if I remember correctly for this homework problem, is they did e to both sides. So we do e to both sides. We have e to the y minus x plus c is equal to y plus 3 over x plus 4 to the 5th power. If I'm not mistaken, I think the answer looks at least something like that, or maybe at worst you have to do one more step of algebra to get to the answer you see. So oftentimes any algebra you need to do after the problem is over involves either using log rules or maybe combining fractions in some way. That's another common technique we've had to use, at least when it comes to algebra. All right, so I'm pretty sure I got this one down. I don't think there was an initial condition, so we can't figure out what C is going to be here. All right, so we have a question, is dy dx equals x linear? And the answer to that question is yes, this one is linear. So let's see why that is. So remember, a linear equation, at least a first order one, the only rules that you have to satisfy are that the y's and the dy dx's aren't touching each other, and also any appearance of those is only them to the first power. Like we can't have like sine of y or dy dx squared. And technically for this equation, we have dy dx plus 0 times y is equal to x. And the derivative and the y aren't multiplied together, and we don't have any of these raised to a power or sine or ln of these, and we have a function of x over here. So this is definitely going to be a linear equation. So this one's also, actually dy dx equals x is actually a lot of, well, it's at least 2. It's also separable, so that's another way we could solve this as well. If we can bring the dx over here and then integrate. Sorry, I gotta drink some more. All right, so that one definitely is linear. Let's see. All right, we have another screenshot here. Let me take a look at this. Okay, so this one is from the Lecture 8 homework. So let's take a look at this guy. So Lecture 8 had to do with equations that were almost exact, but we need to multiply them by an integrating factor. All right, so let's take a look at this guy. So we have 3 plus 3y squared plus 3y cubed dx plus 2xy plus 3xy squared dy is 0. Okay, so let's try to solve this equation right here. So first of all, it's written in the exact form already, where we have something times dx plus something times dy. So we may as well check to see if it's exact as is. And since this is from lecture 8, it probably won't be. But we should, in practice, kind of do that to see if we even need to bother with the integrating factor. So remember, whatever's next to the dx is our m. Whatever's next to the dy is our n. And it actually doesn't matter what order these are written. The m is always the thing that's next to the dx, and the n is always the thing that's next to the dy, in case you see the dy written first. So remember, the partial derivatives we need to check are partial m, partial y, and partial n, partial x. And I like to think of these as like the opposite partials, because m is attached to the x here, but we're doing a y derivative. So we need to check their kind of opposite derivatives to see if they work out. So let's see, the y derivative of m, well, the derivative of 3 will be 0. The derivative of 3y squared will be 6y. And then we have 9y squared for that. And then now we're going to look at partial n, partial x. Okay, so let's see. We're going to do the x derivative of this, so y just counts as a constant. So for this one, we have 2y plus 3y squared. Okay, now the issue here is that these are almost exactly the same, but the problem is that they're off by a multiple, and they need to be exactly the same in order for this to work. So what we're going to do is we're going to take a look at one of the two different integrating factors we often have for these almost exact equations. And the one I'm going to take a look at is the one where we look at nx minus my over m. And our goal is to see if that's just a function of y. So I'm going to look at nx minus my over m, and we're going to see if that's going to be a function of y. All right, well, let's see here. So nx is this, 2y plus 3y squared, and then my, so it's minus 6y minus 9y squared, and then we divide by this one, 3 plus 3y squared plus 3y cubed. All right. Let's see, looking at this one, yeah, this does look like it's going to be a function of y, although, so we could use this complicated thing as an integrating factor. But remember, what we need to do for the integrating factor is do the e to the integral of this stuff. And I don't know about you guys, but I really don't feel like doing some kind of partial fractions with a cubic on the bottom. So why don't we try looking at the other option for integrating factors, where we look at these guys flipped around, so my minus nx over n, and we try to see if this is a function of x. So this was technically possible. That would be really ugly. So this is what I was talking about in the beginning. There are often multiple ways to do something, but we want to avoid doing it the hard way. So I don't want to integrate that. So looking at this the other way, we have 6y plus 9y squared minus 2y minus 3y squared, and this will be divided by 2xy plus 3xy squared. And our goal is to see if this is just a function of x. Now, it doesn't really look that way at first, but we can actually do some simplification to get it to be that way. All right, so let's do that here. So let's see. So I have 6y minus 2y. 6y minus 2y gives me 4y. And then 9y squared minus 3y squared gives me 6y squared. Now on the bottom here, I have 2xy plus 3xy squared. Now, if I look carefully at the top and bottom here, I see that they do actually have something in common. And that's this 2y plus 3y squared. that goes into both the top and the bottom. So if I factor that out, I'm just going to have a 2 on the top. If I factor that on the bottom, I'm going to have x. So I kind of look for what's known as the greatest common factor between these two, and then I factor that out both of them. And since these are the same, these will cancel out. And this function is really the same as 2 over x. So this is just a function of x, so we can use this to make our integrating factor. Remember, this itself isn't the integrating factor. We need to do e to the integral of this first. So e to the integral of 2 over x. This ends up being e to the 2 ln of x, like that. But then this 2 can be the power of my x, so it didn't matter that I didn't include the absolute value, and e and ln cancel out. So when all is said and done, my integrating factor is going to end up being x squared. So that's going to be the integrating factor here. All right, so we have a message saying that they get how to do the rest of the problem. Yeah, it's often kind of hard to figure out what the integrating factor is in doing the algebra. Once you get this down, all we need to do is multiply this by the original equation, and then we're just back to doing an exact one, which are those are on the easier end of things. So that'd be good. All right, let's see. Lecture 9, homework question 3. Why don't we take a look at that? I don't have that available right now. Let me pull that up real quick. This is from Homogeneous and Bernoulli. Okay. Homework 9, number 3. Okay. There's all this stuff. Okay. So for this one, we have 3x squared minus y squared dx plus xy minus 2x cubed y to the negative 1 dy is 0. Okay, so this one's kind of written in the exact form, or maybe exact with integrating factor form already. So it's tempting to kind of try to do it that way. And I would actually recommend doing that in general. But this is from the homogeneous section. So we might as well get some practice doing these homogeneous equations for the unfortunate case when we need to do them, and then we need to do them. So what I'm going to do is to get these into homogeneous form, you kind of write it like as you would a separable equation, where you have dy dx on one side, and then all the rest of the stuff on the other. So I'm going to do some algebra to get that to be the case. So let's see here. I'm going to end up having 3x squared minus y squared with a negative, and then I have xy minus 2x cubed y to the negative 1 is dy dx. And where I got all that stuff from was I subtracted this term to the other side, giving me a negative, which I put over here, and then I divided this term back over here, and then I divided the dx to the right side. The moral story is if you do a little bit of algebra, you can end up getting this equation right here, which I'm actually going to change and distribute the negative signs. We have negative 3x squared plus y squared. Now, one giveaway that, what was I going to say? Yeah, one kind of giveaway that this is a homogeneous equation, and we can use that method to do it if we have to, is notice that all of the terms are to the second power. Like these are to the second power, and then if we combine these powers together, x and y, 1 and 1 makes 2. And if we combine 3 and negative 1 together, that also makes 2. A homogeneous equation will always have each term have the same combined powers. And in this case, it was 2, but it doesn't really matter what power it is so long as they're all the same. If they are all the same, then it's going to be a homogeneous equation. And we actually have a question. Yuru, were you talking about the screenshot you sent, or are you talking about the one we're working on now with which integration method we should use? Because for this one, okay, all right, screenshot. I guess I'll get to that in a minute then. But with this one, I would have tried exact first, but since this is from the homogeneous homework, we should probably try to do it that way. Now, the way homogeneous equations work is we divide both sides by, let's see, our goal is to get a bunch of y over x's to appear in our equation. And what we do is we divide by the biggest power of x that ends up appearing here. Actually, that would be the case if this were to a positive power. Let's see. Oh, in this case, we're just going to multiply the top and bottom by 1 over x squared. It's to whatever the degree that all these terms were. So if I multiply the top and bottom by 1 over x squared to get this into the right form, then what do we end up getting? Well, let's see. Negative 3x squared times 1 over x squared will just be negative 3. And then I have y squared over x squared. And on the bottom, I'm going to have a y over x minus 2x over y. That's going to be dy dx. So you need to divide by x to whatever power that all of the terms share. Since that was 2 in this case, I divided by x. Now the next step is to do a substitution. So the substitution we always do for homogeneous equations is the same every time. It's going to be v, our new variable, is y over x. We need to do that. Now we can't just replace all these with v's and then make that be a dv dx. We actually need to see how this derivative is going to change. So if I multiply my x over here, I have v times x is y, and then I take the x derivative of both sides, I have dv dx times x plus v times the derivative of x, which is 1, is dy dx. So it's tempting to just put dv dx in here instead, but you actually need to put x dv dx plus v on the other side. And unfortunately, that's what ends up making these guys kind of complicated, or these extra terms that end up popping up. So let's convert everything into v's. So let's see, a negative 3 is still just a negative 3. Y squared over x squared will be now just v squared. Y over x is going to be just a v. And then x over y, if we see that, that's going to be 1 over v, since it's the reciprocal. So this is going to be 2 over v right there. And on this other side, we have x dv dx plus v. Okay, so now we've converted our differential equation into v's. And then this is where the trouble begins, because now we need to subtract this v over, combine the fractions, and then divide by an x, multiply by dx, and then move all that stuff over to the other side. So now we're out doing algebra time right now. So I subtract v over v minus 2 over v, and then minus v is x dv dx. All right, and then in order to get that v to combine with the rest of the fraction, I need to multiply the top and bottom of this by the denominator. So let's see, so I have negative 3 plus v squared minus v squared plus 2 over v minus 2 over v. So I multiplied the top and bottom of this v by v minus 2 over v. And then finally, I could do some subtraction. And we got very lucky in this case. Thankfully, the v squareds end up canceling out. We're not always so lucky. A lot of times they'll end up sticking around. But in this case, we did get lucky. So those will go away. And then we have negative 3 plus 2 is negative 1. We have v minus 2 over v down there. That's going to be x dv dx. And then now, if we did everything correctly, what we should have at this point is a separable equation. So kind of like Bernoulli or exact with the integrating factor, homogeneous is essentially separable equations, but with an extra step. Well, quite a few steps. We've already been working on this a while. So now we just need to solve this separable equation and then convert it back again. So I'm going to move the x's over to the left here. So I have dx divided by x. And then that's going to equal v minus 2 over v over negative 1 dv. Okay. Oh, I have a question. How did I get this last step? Are you talking about this right here with negative 1 over v minus 2 over v? Or were you talking about this right here? Oh, so the way I got this was so I had v, right? And I wanted to have this denominator here. So technically what I did is I multiplied it by v minus 2 over v divided by v minus 2 over v. And then the denominator is going to be exactly this. And then the v up here will be v times v will be v squared. And the v times negative 2 over v the v's will cancel and we'll just get 2. So that's where this stuff appeared. And then since they had the same denominator, then I ended up combining those together. That's kind of what was going on with the algebra right there. All right. So now, thankfully, this is an unusually kind homogeneous equation. Usually they don't go this nicely because this -1 will end up just flipping the signs of these two. So this will be a plus, that'll be a minus. So this isn't nearly as bad as it usually ends up being, because typically we'll have some kind of denominator there, and then we'll need to do partial fractions for that. So we've got very lucky with this one. This is a very tame homogeneous one. So now we're in separable mode, so we're just going to integrate both sides, and thankfully we don't need any calc 2 for that. The integral of 1 over x will be ln of absolute value of x. And then over here we have negative v squared over 2 plus 2 ln of absolute value of v. And then maybe I'll just put the plus c over here. It doesn't really matter where we end up putting that. And then at this point, it ends up just becoming a bunch of algebra to figure out what the true solution is going to be. Although, actually, it doesn't look like too much algebra here. The main thing we have to do is substitute back in. So kind of like how when we did u substitutions in Calc 2, we didn't just end things with u. We don't want to just end things with v right here. So what we're going to do is we're going to change the v's back to x's and y's. So ln of x is already an x. Remember, v is y over x. So this is -1/2 y squared over x squared. And this is 2 ln of absolute value of y over x. All right. And then all we need to do now is just move this ln of x over here. And then we have c is negative ln of absolute value of x minus 1/2 y squared over x squared plus 2 ln of absolute value of y over x. And let's see, does this match up with any of the answers right here? Looks to be pretty closely resembling the first answer for this. So that'd be our final solution for this. Although if you were writing this on paper, of course, you could have just left it like that because it's still an implicit solution. The y is negative. All right. I think we have a little bit of a backup here with questions. If I don't happen to get all your questions, feel free to email me them. And I'll be checking my email throughout the day, so I'll try to answer those as soon as I can, if I don't get to all of them now. Let's see. Answer Joseph's question. All right, let's see. Anais has a question from homework 6. Let's take a look at that. All right. All right, so we're supposed to solve dr dt plus r times tangent of t is equal to 5 secant times tangent. So let's write all that out rather than saying it verbally. All right. Let's see. R tangent of t is 5 secant of t tangent of t. All right. So first of all, this is from homework 6, and homework 6 was talking about linear equations. So it's very likely that this is a linear equation, and indeed it is. We don't need to know it's from homework 6 to see that. We have this derivative on its own right here, and then our dependent variable r, that's not multiplied by any other things that have r in it. It's only multiplied by the independent variable, or tangent of t. And then finally, on the other side, we only have at most functions of t. No r's appear up there. This definitely satisfies the criterion for being a linear equation. Looking at this, don't think this is going to be separable, or I can't really see anything else it might be off the top of my head. So I'm just going to go with linear for now, since that is one of the easier methods to do. So the way we solve linear equations is first we get it into this form, where there's nothing next to our derivative and there's all the things that only have t are on the other side. So we're already in standard form. But if we weren't that way, we would need to get it in that way. So if we had like something times here, we would divide by that first. We've already done that. So now what we need to do is we need to figure out what's called the integrating factor. And the integrating factor is always going to be e to the integral of whatever is next to our r, or our dependent variable. So in this case, our integrating factor is e to the integral of tangent. All right. Well, so let's see here. So let's kind of dig out our trig knowledge. This is one of the integrals that I said we might need to know about. The integral of tangent. So tangent is sine over cosine. So if we do the integral of that by a u substitution, we would end up getting that the integral of tangent is e to the negative ln of cosine of t. That's going to be the integral of our tangent. So you can memorize that, or you could do a u sub with sine over cosine to get that as well. Also, some people write this as ln of secant. That's actually the same function altogether. Actually, I'm going to write it that way. I'm going to get rid of this negative. I'm going to make this a secant. Okay, so there's our integrating factor. And what will often happen with these integrating factors is the e and the ln that we get will cancel out. So, and that's going to happen here. So the e and the ln cancel out, and we just get secant of t. Now, what do we do with this once we get it? We multiply the entire equation by whatever the integrating factor is. So I'm going to multiply this whole thing by secant of t. So I have secant of t times dr dt plus r times tangent of t secant of t. And that's going to equal 5 secant squared of t times tangent of t. Okay. So now that we've done that, this is probably the most kind of confusing stuff that most people find for doing linear equations, because you might think we have to do a derivative, but that's not quite what we're doing. What we do now that we've multiplied by the integrating factor is we look at this left-hand side. And at first it looks kind of complicated, but if you stare at it long enough, you'll realize this is actually the result of a product rule. So we're not doing a product rule. We're simply observing that this could come from a product rule of derivatives. And what product rule does it come from? It comes from the derivative of r, or our dependent variable, times the integrating factor. So this left-hand side, this is actually the exact same thing as d dt of the dependent variable r times secant of t. And then I still have this other side here. And that's kind of the crucial step, because we're not taking a derivative of both sides. Otherwise, this would have ended up changing. We're simply recognizing that this left-hand side is the result of a product rule. So we're just rewriting this as a product rule. And if it seems weird, and if you don't believe it, just feel free to go backwards. So do the product rule with this, and then you'll see that we end up getting this down here. And that's actually a good way of checking work too. So now that we've recognized that this is a derivative, well, what's the main way to undo a derivative? It's going to be taking an integral, and that's what we have to do for most differential equations. So we're going to integrate both sides of this. So as we learned in Calc 1 by the fundamental theorem of calculus, the integral of some kind of derivative ends up just being the function itself. They more or less cancel out. So we're going to have r times secant of t on this side. And then we actually need to integrate this. So we need to integrate 5 secant squared times tangent. And this one's going to involve a u sub. So the u sub I'm going to do here is u is tangent of t. And then remember, we can't forget about the du. The du will be secant squared of t dt, which conveniently shows up in the integral. So this will end up being the integral of 5 times u du, because the tangent turns into u, and then secant squared dt turns into du. Then we just do this integral, which is a power rule. So it's 5 halves u squared, and then we have our plus c. And then remember, u, we can't leave it in terms of u. We need to have our function in there. So this is r secant of t is 5 halves tangent squared of t plus c. And then finally, we could divide both sides by secant, or in other words, multiply both sides of cosine, and then we can get our final result for this. That's going to be how we're going to finish this guy up. And I think it ends up being the first answer choice that we have there. All right, so that's an example of a linear equation here. So that's good practice. Let's see, I may have time for one or two more questions. But as I said earlier, feel free to email me if I can't get to all. All right. Let's see. So the next one is from Yuru. Let's see. All right. Oh, so this actually isn't about solving the question. This is about doing which method to use. So if you look at the screenshot that Yuru sent at 11:36, it's one of those exact ones with where you need to multiply by the integrating factor. And the question asks us, what type of equation it is, and it ends up being that you can have an integrating factor of either variable. And what Yuru is asking is, which way should we do it if we have it with either variable? And my answer to that is whichever one would be easier to integrate. So if you were here earlier and you saw when we did that one integrating factor one, we also could have done that one both ways, but doing it the y way would have had us integrate that crazy rational function with y. But doing it the x way, we just had to integrate 2 over x. My answer to that is you could do either one, but I would strongly recommend you pick whichever one is easier to integrate. That would be my answer to that for picking which method. That's how you want to do all of these. If you want to make things easy on yourself, you got to pick the easiest way to do it if there are multiple ways. All right. Let's see here. Okay, yeah, so a follow-up question to that. If exact or exact integrating factor doesn't work, then we should try homogeneous or Bernoulli. Yeah, so I kind of gave like a hierarchy of like different methods to try, with separable usually being the easiest, and then maybe exact and linear are a bit more complicated, but usually pretty easy. And then below that would be exact with the integrating factor and Bernoulli, which will lead to the 2 easier ones. And then as a last resort, we can do homogeneous, because even in the very easiest, like that example I did a few minutes ago is one of the easiest possible homogeneous ones, and even that took a lot of algebra. So I would really recommend not doing homogeneous unless you really have to. So that one's like the last resort. All right. So let's see here. I have a question from Naomi. Let's see. Lecture 5, number 9. Open this up. Okay. So this one, since it's from lecture 5, that means we're probably going to end up doing a separable equation. So this separable equation ends up looking like dy dx is secant squared of y over 1 plus x squared. Okay. We can definitely see that this guy is separable because we have some function of y times some function of x, which is actually 1 over 1 plus x squared. So it's pretty clear we could split apart the x's and y's. So this is definitely a separable equation. So first we need to get it into the right form where we have all the y's on one side, x's on the other. So I'm going to bring the dx over here. I'm going to bring the secant squared down there. So I have dy over secant squared of y is dx over 1 plus x squared. All right, now 1 over secant squared of y, I guess I could leave it like that, but it's probably better to think of it as cosine squared. So I'm going to rewrite this as not 1 over secant squared, but rather cosine squared of y. And then now I have it written that way, then I'm going to integrate both sides of this. So I'm going to integrate here, I'm going to integrate here. This integral right here, this is exactly the one I was warning you guys about earlier. This integral shows up all the time. Like if you're ever going to see an inverse trig function, there's at least like a 95% chance it's going to be arctan, and it's going to come from 1 over 1 plus x squared. So hopefully you see that the right side will end up integrating to arctan of x plus c. This one shows up often enough. That one's definitely worth just straight up memorizing. This one shows up all the time. Now over here, this is probably a little bit trickier than the integrals we usually see. We have to integrate cosine squared. And this might bring back horror stories from Calc 2. How do we do that? Well, with cosine squared, or even powers of sines and cosines, we have to use what's called the half angle formula. So the formula for that is 1/2 times 1 plus cosine of 2 times y. And then rather than integrating the original function, we instead integrate this instead. Now, like I said, don't worry about this for the exam. I mean, more complicated integrals may show up on homework, but at least there you can look up stuff. So don't worry about memorizing the half angle formula for the exam tomorrow. But then how we would finish this off, we would just integrate 1. So we have 1/2 times y. And then the integral of cosine of 2y over 2 would end up being sine of 2y. And then we divide by another 2, so it's 1/4 sine of 2y. And then we already have the plus c on the x side. So, and then there's no way to solve this straight up for y. So honestly, this is kind of the best we can do here, having this implicit solution. All right, so that's it for that separable equation. Let's see. All right. All right, can you go over the practice exam number 23? Yeah, sure. That'll be my last question. So let's see if I can pull that up real quick. Exam. All right, and then number 23. Okay, so this one, let's see, what do we got here? So we're just supposed to solve the differential equation. So we have x dy dx, let's see, minus 1 plus x over x times y is equal to x y squared. So we're supposed to solve this equation right here. Now, looking at this, this almost seemed like it's a linear equation, right? But there's actually one difference. So this part's okay with the linear. I mean, we're going to need to divide by x, but other than that, it's okay. This is a function of x times y. That's fine. But then this part right here, we have y to a power. And you're like, okay, that definitely messes it up for being linear. But there's a type of equation that's very similar to linear called Bernoulli, where it's actually okay to have y to a power on this other side. So technically, this is a Bernoulli equation. So what we're going to do here is first I'm going to get it into linear form, at least as close as we can. We're going to divide by this x. So minus 1 plus x over x squared times y is equal to y squared. And then what I do next is I'm going to make a substitution. Now the substitution involves whatever power we have for the y on the other side of the equation. Depending on what number that is, that's going to affect my substitution. My substitution will always be v is y to the 1 minus whatever that number is. So in this case, since it was 2, I have my substitution is going to be v is y to the 1 minus 2, or y to the negative 1. So v is going to be y to the negative 1. So if v is y to the negative 1, that means that v to the negative 1 is going to be y. So in order to get what this derivative is going to be, I need to take the derivative of both sides of this equation. So when I do that, I have negative v to the negative 2 times dv dx is dy dx. And how did I get this more complicated bit over here? I did the chain rule. So the derivative by the power rule of this will be negative v to the negative 2, but then v depends on x, so I need to multiply by dv dx. That's one common mistake with these substitution type methods. Your derivative won't just be the derivative of the new variable. It'll actually have extra stuff along with it. All right, so now let's convert this equation into v's now. So dy dx, we just said that was negative v to the negative 2 dv dx. All the stuff x's will stay the same. But y, remember, that's going to be v to the negative 1, so it's 1 over v. And then y to the negative 2, that's going to be v to the negative 2. All right, so now we've converted our equation entirely into v's and x's. And then what we're going to do is we'll find out pretty soon this is actually a linear equation. So I'm going to get dv dx on its own. And to do that, I'm going to multiply everything by negative v squared to get that to happen. So I have dv dx plus 1 plus x over x squared times v. And then multiplying by negative v squared here will actually just give me -1 on that side right there. All right, and then now that I have this, this actually ends up being a linear equation. So now we just have a nice linear equation for us to look at. So this guy right here is going to determine what the integrating factor is going to be. So it's always going to be e to the integral of whatever this stuff is. Like that. All right, so this integral actually looks a little bit more complicated than usually what we see for these types of problems. So let's see how this is going to pan out. So I'm going to divide both of these by x squared. So this is really e to the integral of 1 over x squared plus 1 over x. And then when I do that, I get e to the -1 over x plus ln of absolute value of x. And then when I combine these guys together, then let's see, what am I going to get? So if I get rid of this, if I simplify this guy right here, I end up getting x e to the -1 over x, because the e and the ln x cancel out, but I still have this e to the -1 over x I need to use. So that's going to be my integrating factor. I'm going to multiply the entire equation by that. So I take this equation and multiply it by my integrating factor. So I have x e to the -1 over x dv dx plus 1 plus x over x e to the -1 over x times v. And I have negative x e to the -1 over x right there. All right, and then to finish this off, what we would do is we would recognize that this is a product rule right here. This is the product rule of our integrating factor times our v. And we still have this over here. All right, and then we finally need to do the integral for this one. So if we do the integral over here, we have x e to the -1 over x times v, because the integral of the derivative is whatever it is. Okay. And then we're going to need to do the integral of -x e to the -1 over x over here. Now for this one, this looks like a pretty tricky integral, and this actually does end up kind of being tricky. The way I would do this is I would do a u sub with u equaling -1 over x. So if I do this, then my du will be 1 over x squared dx. But the thing is that I really want there to be a, I want there to be an x dx in my numerator. So what I'm going to do is I'm going to multiply both sides by x cubed for this guy. All right, so I have x cubed du is x dx. But then what is this going to end up being right here? Actually, wait a minute. Wait a minute. Oh my God. I made a mistake really far back. So when I did my integrating factor, I assumed the denominator was going to be x squared, but it was really just an x. I was getting a little worried at this point because this integral is actually going to be really hard to do. So I'm sorry about that. Earlier, let's go back to the integrating factor part. The thing I was really going to integrate should have been e to the integral of, let's see, 1 plus x over x instead. And this will give us a much nicer integrating factor, the e to the ln of x plus 1, or sorry, plus x. So this will be x, e to the x. And then rather than integrating that terrible thing we were doing right now, we're instead going to integrate x e to the x instead. So that, I was getting a little worried. That integral we were doing was pretty hard. It might have been one of those impossible ones. But we're just going to So everything that I did was exactly right, except my integral that I'm doing at the end is going to be this instead. All right, well, I'm out of time for now, but I think I actually got to all the questions here. But of course, if you guys have any other questions, feel free to email me and let me know if you have any other issues. So, all right, well, I guess yeah, good luck on your exam tomorrow. Let me know if there are any issues with honor lock or anything like that. And I'll be happy to help you out. So the best of luck to you guys tomorrow.